So good morning, everybody, and welcome to this 20th webtech of the European Cluster of Ceramics dedicated today to ceramic injection modeling. I'm Alexandra Baudrouet, Project Officer at the European Cluster of Ceramics. So first, I will begin this webtech with a fast introduction of our cluster. We have 140 members in 7 European countries, and one of our missions is the leading of the ceramic network. This webtech is a way for our members to introduce their know-how in these difficult times. Here you can discover our next events, webtech and expert sessions. Please also note that our ceramic network event is postponed in November. During this event, you will have B2B meetings, thematic conferences, and visits of sites. Feel free to contact us about this event if you want more information. Now some recommendations. Before beginning this webtech, please switch off your microphone and your webcam using this icon here. And also log you with your first name and last name. For your question, please use chat at any time. Helio will answer to your question after his presentation. Now I will give the floor to Helio. Helio, you can share your screen now.
Hello, good morning. Can you see my first slide, Alexandra?
Yes, it's okay, Helio.
Okay, so good morning, everyone. My name is Helio Jorge, and I'm the R&D project technical manager at Ctcv in Portugal. So it is a pleasure to be here to perform a webtech in the pool. And I hope that my presentation can be useful for everyone. So first of all, don't know Ctcv, I can introduce my institution. It was established in 1987 by the Ceramic and Glass Industrial Associations and Companies. It is a non-profit organization, and it is one of the centers of the technology interface of Portugal. So our activities are divided in 4 main areas. The one that I come, the innovation and development, technical consultancy, testing, and training. We are located in a city in central region in Portugal. It's Coimbra, and those who intend to visit Portugal can pass through this city. We will find a huge and health cultural heritage because it was one of the capitals of our country. So you are invited to visit our city. In Ctcv, we are 60 collaborators, and we are supplying services for more or less 550 customers last year. We are an accredited organization for supply services under Portuguese financial instruments. Nowadays, we are undergoing participation in more than 20 R&D projects from Portugal through Europe. And we are a member of national and European clusters like the Pôle Européen de la Céramique. So in my department, our mission is to develop technology. So we make industrial research, development, and innovation, starting from the technology readiness level from 4 to the last level 9. So we are talking about starting from lab scale technology validation to system approved in production. So we took the science results from the academic institutions and tried to develop through the industrial level. We make also services in intellectual property and technology transfer. And of course, we used to participate in many R&D funded projects under Portuguese framework and also under European framework. So these are the 3 topics of my presentation here. I will introduce the ceramic injection molding technology. I will go through some details in the process steps, and in the final, I will present some ways of collaboration with Ctcv in this area. So let me tell you what is an overview about powder injection molding technology. So it is a group of technologies for component production. We can process metals, ceramics, and cemented carbides. So ceramic injection molding is one of the fields of powder injection molding, as you can see in this scheme. So there is some boundary conditions to look for a part for ceramic injection molding. Usually there is a rule term that tells that the part can be inside a tennis ball. So we are talking about a part up to 125 grams in an aluminum in the case of ceramics. And there is some limitations in the maximum length. We're talking about 100 millimeters. In terms of production volume, there is two divisions of ceramic injection molding. When you're talking about the process with high pressure injection molding, we are going for high production series, starting from 10,000 parts per year. Okay. When you want to go to the low level, less than that figure, we can use low pressure injection molding technology. I will talk about these two types of machines. So this is the process flow, starting from powder and ending in the sintered parts. And generally, we can find four main advantages in ceramic injection molding. It is a one-step shaping of very small part geometries. It is a cost-effective production route for difficult machinable materials. And again, it is applicable from low to high series production. And usually in the shaping step, we are talking about use up to 100% of raw material. So we are virtually non-scraps in the shaping step. So how to consider a component as a ceramic injection molding candidate? So this is a table, a generic table to consider, to look for a part and to see if it can be produced by ceramic injection molding. Usually we are talking about the maximum limits. If we have alumina parts, we can consider maximum of 125 grams and the wall thickness of 8 millimeters and the maximum linear dimension of 100 millimeters. Okay, but if we want to find out the correct part for ceramic injection molding, we need to join to these geometrical types or issues. We need to have complex shapes. We can make 3D forming design, and we can integrate multifunctional aspects in the same part. It is very important to make the ceramic injection molding technology very competitive against the other technologies. Of course, there are some rules that we can use to make the production process easier, okay, and to reduce material consumption. For example, we can redesign the parts, and we can take a part that is made from press and machining, and it is very costable. There is a high cost of that technology, and we can make some redesign manipulations and put it to ceramic injection molding. And we can use these rules to reduce material consumption, to turn the parts more functional, and of course, to make the part more market competitive. Okay. So in terms of materials, for ceramics, we are talking about oxide ceramics that are the main majority of materials that in the market are transformed by ceramic injection molding. We're talking about alumina, zirconia, and the composite between these two ceramics. It is also possible in nitride ceramics, and it has been done, and silicon ceramics like silicate ceramics like steatite and porcelain. So by here it is possible to apply this technology to any ceramic that is sinterable, let's say. So these charts tell us what is the application areas in terms of production quantity, and shape complexity. So the ceramic injection molding is in this corner of the chart, where we have a high complexity of component shape and high production series. Okay, and here you can see one of the difference. The difference between the high pressure ceramic injection molding and low pressure ceramic injection molding. Again, the difference is about the quantity of production. What is the application of the ceramic injection molding in terms of kind of parts? So we are talking about machinery parts, automotive industry, medical instruments, electrical tools, watches and jewelry, microsystems, electronics. So it is a wide range of application sectors. Okay, it's a very flexible technology. Here you can see four examples of parts. This is alumina casting cores. It's a very old application of ceramic injection molding. When you are production turbine blades in metals, namely in inconel alloys. This salt grinder is also a very typical product or parts produced by ceramic injection molding, as well these zirconia watch parts, okay, very found in the market, and also typical example in textile machinery parts. Okay. So any kind of application where we found wear, high temperature, and of course, if you see here, there is a lot of complexity in the part design. So let's go deeply in the production process steps. So again, we see that we start from the feedstock, that it is a mixture between the powder and the polymeric additives, and we shape it by injection molding. Then we remove the majority part of the binder, and then go to sintering process, and we get it our final part. This final part is a sintered state, but can be finished by the conventional technologies, like grading, polishing, and any kind of hard machining. It is possible to finish the parts. So the first step is the feedstock compounding, and let me tell you that if a company wants to go for ceramic injection molding production, it can choose between two ways: to produce the feedstock in-house and to go into the market to buy the feedstock ready to mold. Okay, so this step is it's not obligatory. They can choose if they want to invest in feedstock compounding or to buy the feedstock outside. So in this process, we mix the powder in the binder. So it is a warm, hot process, and we want to homogenize the powder through the binder and to get the feedstock in granulate form. Usually we use ultrafine powders in ceramics, so usually less than 1 micrometer. About the binders, the binder is a multi-component polymeric-based mixture, and it should be tailored for the specific ceramics. Mainly the dispersion and additives are found to be different from powder to powder, or at least from the oxide ceramics to nitride ceramics. So we have to choose and to find and to develop the right binder composition for any kind of the powder. Okay, so the feedstock is a very critical component in this technology, and I will point some aspects of the feedstock. So we have to optimize the solid concentration. We don't want to have excess binder nor excess powder. We have to find out the precise optimized concentration. Of course, we have to have homogeneous dispersion of the powder through the binder matrix. So it is very critical in the mixing step. We have to have rheological properties adequate for injection molding. Usually, we can find this relationship between the viscosity and the shear rate. And we are talking about pseudoplastic behavior of the compounds. And of course, we have to promote, to plan for a fast debinding with no part defects. So when we are developing the binder, we have to put our mind through the debinding as well, to avoid part defects and to speed up the debinding as fast as possible. And of course, we have to promote a high density of sintered material with no part defects. And the binder can be critical for this issue as well. And at final, of course, we have to find out the right sintered materials, properties, in order to accomplish the part specification. So in injection molding step, we process the feedstock by melting and cooling down inside the tool. And then we get the green parts, the molded parts after this step. So the injection molding, it can be performed with this kind of machine. In this scheme, we have a high pressure injection molding machine, which is very similar to, has plastic injection molding machines. We got the tool inside, and we have the plastification unit here. And in this machine, we have the injection molding cycle that is composed because in the movements of the machines and the filling of the tool, the packing of the feedstock inside the tool, and then the cooling of the part inside the tool. And then, of course, the tool will open up and extract by a robotic arm. So this is a very high pressure injection molding machine is a very productive way to manufacture the parts, like in plastic injection molding. Here, we can split the injection molding step between two kinds of steps. It depends on the machine that we use. If you use this kind of machine, a floor stand machine and a big machine, and we use big steel tools with hundreds of kilograms, so we're talking about a cost of tool comparatively high. So that's why here we can use this technology for large production capability. If you use this smaller machine, which is a benchtop machine, we use pressures of injection molding lower than 50 bars. And then we can use very small tools, not so complicated like these ones in high pressure. You can see here what is the size of a tool compared to the hands of the operator. And so the tools are not so costly, and then we can make prototyping, and we can make short production capability. So it depends on the strategy of the company, and it depends on the production series for the part in question. Here we have a comparison between two tools, between the high pressure injection molding and the low pressure injection molding. And here you can see in the same claim what is the difference we are talking about against high pressure and low pressure. And that's why we have a high expensive tool in high pressure and low expensive tool in low pressure. Okay? So the cavities of the tool should be oversized to compensate the shrinkage during sintering. You can see here an example what is the range of shrinkage in alumina. We're talking about between 15 and 25% of linear shrinkage. And of course, if there is anyone in the assisting this presentation from plastic molding industry or for tooling, the tools are, let's say, 50% similar to plastic molding, but there is a critical aspect to change from the plastic world to the ceramic injection molding tool. So the next step of the process is debinding, where the binder is removed by several different methods depending on the specific binder's chemistry. So I will present the common methods to remove the binders. There are some binders composed by wax and polymers that can be removed by thermal way, and where the parts are warming up until the polymers start to degrade by a thermal way. We can remove the binder by a catalytic method. This is applied for the binder based in polyacetal or polyoxymethylene. And so the parts are warming up in acidic atmosphere, but the temperatures here are more or less 100 degrees, when in the thermal way we go through 300 degrees, 400, 500, 600 degrees. So this is a quite quick method for removing the binder. And there is seven other methods. Solvent method, when we have a wax and a polymer again, but the wax is soluble in organic solvent. So we put the parts immersed in organic solvent and wait for the dissolution of the wax part. And when we have, when the soluble component is soluble in water, we can use water immersion method, which is more eco-friendly, more environmental friendly process. Here we can see the green parts in the left picture and the brown parts after the debinding in thermal way. After debinding, we proceed in the last step, sintering, which is very common in ceramic world, as everyone knows. And typically we have a thermal profile starting in the one phase of remaining of the binder burnout. So in the debinding phase, we remove not the whole part of debinding. We keep some 5 to 20% of the binder to go through the sintering furnace in order to retain the shape of the part. Okay, so we need to slowly heat up the parts and wait until the binder is burned out in the first phase, and then go to the high temperature and perform the sintering, as I think everyone in this audience are experiencing this. Okay. The last part is how can Ctcv can collaborate with people from universities, from companies, from other kind of material world. So this slide represents a short figure of our experience. This is a collection of parts that we have made through the last years, from the household and personal parts, machinery parts, metal wire guides, textile machinery. So we are experienced, to be honest, in alumina and zirconia, and both in the composite of these two materials. And also we have here a tungsten carbide that we can consider like a ceramic one because of the hardness. We have some experience as well in cemented carbides with cobalt as the binder. Okay, and you can see how much tiny we can mold the part and go to the maximum of the size permit allowed in ceramic injection molding. Here we have an example of a list of machinery that we have in our PIM pilot plant. We can do feedstock compounding using two machines. We can do molding, high pressure injection molding and low pressure injection molding, as I told you before. And we have all the methods of debinding through catalytic, thermal, solvent, and water. And we can perform, of course, sintering of ceramics. And let me point out this little item. We can also make metal injection molding and especially the sintering of metals. If everyone is, if there is someone interested in metal injection molding as well in ceramic injection molding, I can tell that we are also working on that. Of course, we have a huge list of R&D equipments and laboratory equipments for service providing. In ceramic injection molding, it is very critical to control rheology and to control the powder as starting material. And of course, there's a huge number of techniques for laboratory characterization. So, let me list some of ways of Ctcv partnership. So we can develop new materials for ceramic injection molding, starting from feedstock to sintering, and go through all the process. We can test the technology and to produce samples for companies who wanted to test new part production. We can simply make the material characterization and testing, of course. We can make tool processing, so we can be contracted for compounding, or for debinding, or for molding, or for sintering, okay? And we can support in mold concept and design. If there is a company or a laboratory that have all the facility but don't know exactly the technology and how to design the tool, we can support in this area. At last, our powder injection molding pilot plant we can use for technology transfer to industry, and of course we can support starting up a new business in powder injection molding as well. We never forget all these ways of partnership we can do if you want to go to large production series with high pressure injection molding, or if you want to go low pressure injection molding technology to low production series. Sometimes it's a question of decision, or sometimes it's an opportunity of manufacturing of a certain part. If the part is for low series, we choose low pressure. If it is for high production, we go for high pressure. And of course, not only ceramics. I'm sorry, I can advertise some other materials. Ceramics, and if there is someone interested in go to metals and cemented carbides. Okay, so this is my last slide. I hope this presentation would be useful for you, and I am at your disposal to answer some questions that are allowed.
Thank you very much, Helio, for your presentation. So we have several questions. The first one, what are the suitable wax polymer powder proportion in the case of alumina, for example?
In the case of, I didn't understand the end.
Alumina.
Alumina. So usually we are talking about, so in polymers usually is used polyolefins. So polypropylene and polyethylene mainly. And waxes, there is a lot of options, because waxes has low viscosity and high viscosity, but also we can go easily to polyethylene wax. Okay? Concerning powder proportions, it depends on the particle size mainly and the morphology. So we can go starting from 55% in volume to 60%. I'm sorry, I cannot tell a definitive number because it strongly depends on the alumina powder characteristics.
Okay, thank you, Helio, we understand. We have another question. What kind of solvents are you using for debinding phase?
Organic solvents. So hexane, acetone, ethanol, isopropanol, that kind of solvents, and water.
Okay, thank you. I have another question. What is the usual porosity level you have just after sintering phase? And do you use sintering under pressure to reach lower levels?
So the porosity level depends on the material that we are sintering, but usually we're talking about less than 5% for sure, and less than 3% in the main cases. Here in Ctcv, we don't have equipment for pressure sintering, but yes, it can be used. If you want to have 0 or less than 0.5% of porosity, we should use pressure in sintering. Hot isostatic pressing, for example, it depends on the application of the part.
Okay, thank you, Helio. One more question. You mentioned critical differences between ceramics and plastics molds for high injection molding. Could you give some examples about this?
Yes. There are some features of the feedstock that induces through the modification of the tool compared to plastics. First is the viscosity, the wear of the feedstock through the steel of the tool, and the brittleness. And for example, I can give you concerning the brittleness of the feedstock. When we have the parts cooled inside the tool, the material is quite brittle, not flexible like in the majority of the plastics. So we have to have some strategies to extract the parts out from the tool without breaking it. And two strategies is to finish the surface of the cavity or the runners to decrease the adhesion of the part in the tool. And the other strategy is to put more extractors than it is found in plastic. So we have to support more area of the part to push out the part out the tool. Okay, so we have no flexibility and we have less retraction because the plastics has flexibility. And we here in ceramic injection molding, we have let's say 60% of powder, so 60% of the material in volume doesn't shrink when it goes from the melt to the solid state. And because it doesn't shrink, it was easy to get out alone from the tool. So this is my example to you of one critical issue in tool design and two ways to solve. And Florian, if you want to have more support, you can contact me by private message.
Thank you, Helio. One more question. How long does it take to put in form a ceramic piece, including the molding step?
Sorry, can you?
How long
I didn't see this. I don't see this this question in the chat list.
It's a question of Florian.
Okay.
Okay.
Yes. How long does it take?
How long does it take to put in form a ceramic piece, including the molding.
Okay. I think I understood. So, what is the injection molding cycle time? We can talk about 30 seconds. So, in 30 seconds, we can produce 1, 2, or 4 parts in the injection molding machine by high pressure injection molding machine. If we are talking to about low pressure, the things go higher, and we can have 1 minute each injection molding cycle in low pressure injection molding.
Okay, thank you, Helio. And the last question, you mentioned 8 mm as maximum wall cross section for alumina. Is it the same limit with zirconia?
Yes, you may consider that. It's a typical value, okay? It's a typical value. We can talk about 7, 8, or 9. So it's a thumb rule. It's for people that can think to mold 20 millimeters or 30 millimeters part. You cannot do it. This maximum wall section is also because of the debinding process that we need to remove a lot of polymeric binder from the center of the part to the outside. Okay.
Okay.
So you can consider 8 millimeter also for injection zirconia, but at the end of the day, you should test it.
Okay. Okay. Thank you. Do you have another question, everybody? Is it clear for you? So anyway, Helio will send to you his slide deck, and the video of this presentation will be available on our YouTube channel. So please follow our news to know when the video will be available. No more questions? No, everybody say thank you, Helio.
Okay, thank you
very
all.
much. Thank you very much.
Thank you, Alexandra.
You're welcome.
Have a nice day to all.
Have a nice day, everybody.